AP Chemistry, and welcome to More Entropy. more. All right. So here, what we're going to do is we're going to talk about how to use our idea of entropy as the number of microstates to predict whether or not a process is entropically favorable. Okay? So, if we look here, right, we have CO2, solid, versus CO2, gas, right? Do we have more microstates here or here? Ding, ding, ding. Which means that this leads to an increase in entropy. Yes? Okay, so here we have some calcium oxide solid, some CO2 gas, and then we take all of that and we do a synthesis reaction and make some calcium carbonate. That reaction should look familiar, by the way. And we form calcium carbonate. Now, do we increase our microstates or decrease our microstates? Right. This is a decreased number of microstates because we did have a gaseous component, right? Something that had translational and rotational and vibrational motions, and we've confined all of these things now to this new solid, right? Which means that this would be an increase in entropy. This process would be a decrease in entropy, okay? Here we have HCl gas plus NH3 gas come together to make a solid. Same principle, right? Here we have gas. You're like, well, now how do I compare? Well, here it just has to do with the amount, again, of microstates, right? Here we have a 2 and an implied 1, which means here we have 3 moles of gas. And on my product side, we are making only 2 moles of gas, right? And we know, obviously, the law of conservation of mass is applied here, right? Meaning that we have the same total number of particles on each side. But the fact of the matter is that here we have 3 moles of particles all having translational, vibrational, and rotational motion, right? Here, we only have 2 moles of particles having translational, vibrational, and rotational motion, okay? That translational motion being one of the biggest things in terms of entropy, right? Which means that if we decrease our moles of gas, we decrease our overall entropy, okay? Here, we're going to choose the system with the greater entropy. So now we're not looking at a reaction so much as just comparing A and B, or whatever, situations to situations. All right, so here we have 1 mole of H2 at STP, or 1 mole of H2 at 100 degrees Celsius and half an atmosphere. STP is what? All right, that's standard temperature and pressure, which is 0 degrees Celsius and 1 atmosphere pressure. Here we have increased temperature, where if we increase the temperature, we know that they have more kinetic energy, right? And we have 0.5 atmospheres. What's the significance of that? Right, if we still have the same number of particles spread out over a lesser pressure, means that they have a greater volume, yes? Meaning that our 1 mole of particles here has a greater volume to be in, which means that this situation has the greater entropy, okay? All right, next up we have 1 mole of H2O solid at 0 or 1 mole of H2O liquid at 25. Greater entropy, right. I feel like that one's pretty easy. All right, 1 mole of H2 gas at STP or 1 mole of SO2 at STP. What's the only difference here? Right, the complexity of my molecule, right? Here we have 3 atoms that make up my 1 molecule. Here we only have 2 atoms. This one has another bond, which means that this one has more vibrational motion than this one does, right? Which means that this one has greater entropy. Here we have 1 mole of N2O4 versus 2 moles of NO2. This goes back to kind of like this one, right? If we simply have more particles that are able to move, we have more microstates by default, right? All other conditions being equal, more particles means more entropy because there are more microstates, right? More arrangements for my particles to be in, okay? All right, next up. Entropy of hydration, where hydration just means dissolving. This figure should kind of look familiar because we talked about this basic thing at the beginning of chapter 4, right? Where we said the act of dissolving really means that these ions from my solid interact in a direction-oriented way with my water molecules, right? Where the cations selectively get surrounded by the oxygen ends of water, and the anions get selectively surrounded by the hydrogen ends of water. All right, now, from the point of view of my solid, what does this mean in terms of entropy? Right, for the solid, we are definitely increasing the entropy, Okay, my solid has more entropy over here as ions because they now have translational motion, which they didn't have in here. Okay, now what about my water molecules? Right, from the point of my water, we have decreased entropy. Okay, because previously they were free to interact with whatever they wanted to, wherever they wanted to, move across the whatever beaker or flask they were swimming in. Here, though, we are sort of imposing an order upon them that wasn't there before. Okay, by introducing these ions, we are imposing a level of order that wasn't there before, which is why from the point of view of the water, this is actually a decrease in entropy. So when we're talking about hydration as a process, right, the entropy of my process, the entropy of dissolving, is always going to be variable because it depends on which point of view we're talking about, right? And we're going to talk a little bit more about this in class. We're going to look at a demonstration where we're going to talk about will this dissolve and what sorts of things should we be thinking about, okay? Anyway, so make sure you keep that in mind. There are 2 points of view when we're talking about that process. Third law of thermodynamics says that the entropy of a pure crystalline substance, meaning a pure substance, not a mixture, okay? Pure crystalline substance at 0 Kelvin, absolute zero, is 0, okay? So first law states that energy is conserved. Second law states that the entropy of the universe increases for a spontaneous process. The third law says that the entropy of a pure crystalline substance at 0 degrees Kelvin is 0. Now, this one has direct importance because this is how we quantify entropy, okay? So here we have our standard molar entropies. Note that this is not the standard entropy of formation, okay, just standard molar entropy, all right? Wherein 0 Kelvin is kind of like where everybody is 0, right? And then there are a series of experiments that scientists do, the ones who make all the data that go into our little handbooks, right? And through that series of experiments, they can sort of quantify what a substance's standard entropy, right, for 1 molarity, or 1 molar, what a standard entropy would be for that substance at standard conditions, which again, not the same as STP, right, 298, okay? Now, if we look over here, right, some of the general trends that we should notice, right, are one, as we, well, okay, I guess the first thing that you don't really notice, but I'm going to tell you, right, is that there is no such thing as a 0, okay? Nobody has 0 entropy, because we're not at 0 degrees Kelvin, which is the only place that things have 0 entropy, okay? Everything can vibrate, well, if it's a molecule, right? And everything can to some extent rotate unless it's fixed in a crystal structure, but there is some movement happening, okay? Which means that nobody has a 0 for their standard molar entropy, okay? Beyond that, phases are really, really important, which this table is really not great for showing, but again, there's that one at the back of your book or the one that's up on WebAssign, but phases are really important, right? Because like we said, right, solids have less entropy than liquids, have less entropy than gases, okay? Which is why, again, going back to the questions from your guys' last WebAssign, right, one of some of the most annoying problems are, for example, using heats of formation to solve for the overall heat of a reaction, because you have to find the substance, and then you have to find the right phase of that substance. Same thing applies for our entropies, okay? In addition, we also have the observation that as we increase our molar mass, right, we also increase our entropy, all right? And that sort of happens here, like if we look at this series, right, lithium, sodium, potassium, right, all atoms, right, so we're not looking at any change in bonds. They're all atoms, but we notice that as it gets bigger, we have more entropy, right? Why might that be the case? Right, the simplest reason is that we simply have more moving parts, right? Electrons are always moving. As we add electrons, we have more moving parts, okay? So this is just a general trend, right? And again, for larger molecules, as we increase the number of atoms, we increase our entropy, which we saw in that figure earlier, right? If we have more atoms, we have more options for vibrational motion, which increases our overall entropy, all right? Okay, moving along, right, that brings us to this, which should look really familiar because it's just like the equation that you used in Chapter 5. So we can solve for the entropy of a reaction by using the entropy of my products minus the entropy of my reactants, bearing in mind my numerical coefficients, okay? And since delta is always the change, and change is defined as final minus initial, right? Final minus initial, okay? Now, Oh, actually, we're going to pause here. There's a bunch of practice in your WebAssign, so don't you worry, you will practice using this soon. And literally the exact same thing as the previous chapter. All right, thanks for listening. Be good. I'll see you soon. Okay, bye.